it's my pleasure to introduce Bhargav Bhatt, who's going to talk about interpolating between p-adic cohomology theories.
Thank you. Thanks for the invitation. And again, thank you for accommodating my changing schedule this semester. Right, so I want to talk about interpolating p-adic cohomology theories. And so roughly this is a talk on integral p-adic Hodge theory. And that's not going to show up until the end of the talk, but that's kind of where we're headed, so I should at least start off by telling you that.
Integral?
Integral, yeah. And so in the last 10 years, there's been a lot of progress in p-adic Hodge theory that has happened due to various techniques, and one of the goals of this talk is to kind of give you some kind of a survey of what has happened. But I want to get there slowly, so I want to start off with something which is not p-adic at all, and motivate a problem which maybe you can appreciate even if you don't care about the p-adic numbers, and then after that we'll get to the p-adic setting. So let me sort of start off with classical Hodge theory. And so there's various settings in which you can do this. Let me, I'll pick one. So say I start off with a complex manifold, and let me assume it is compact. So some of the goal of Hodge theory is to understand what structures does the cohomology of X inherit by virtue of the fact that it is a complex manifold and not just a random topological space. And so there's like an elaborate machine that helps you understand the structure, and I just want to tell you two theorems that form kind of the starting point of the subject. So the first theorem is the Rham's theorem, which actually has nothing to do with complex structure really. But let me start here. So it says that if you want to understand the singular cohomology of X, so the thing that only depends on the underlying topological space, you can do it through studying differential forms on the space. So there exists a natural isomorphism between singular cohomology of X, and I want to stick to complex coefficients, and it's the Rham cohomology. And again, with complex coefficients. And so, what is the right-hand side? So one way to define it is to think about C infinity complex valued functions on X and form the de Rham complex associated to such objects. So you have C infinity 1 forms and C infinity 2 forms and so on, and look at its cohomology. Since X is a complex manifold, there are sort of other ways of doing it too. You can restrict your attention to just holomorphic functions instead of all C infinity functions. And at least if you use the language of sheaves, you can prove that what you're doing doesn't really depend on that choice. And so this is kind of useful for us because it's telling you that if you want to study the topology of X as incarnated by the left-hand side, you can think about it in terms of the right-hand side, which kind of has more to do with the geometry of X in terms of function theory on X. And it's not just an abstract statement, right? I mean, people have seen this, but let me remind you again how this works. So singular cohomology is the dual to singular homology. Homology is defined in terms of kind of cycles in your space. And so if you want to define an isomorphism from here to here, you need to understand how to pair a homology class against a differential form. And so what is this given by? This is given by the pairing of, so I start off with, let's say, the class of the differential form omega in the Rham cohomology, and the class of the cycle gamma in singular cohomology. And I pair them against each other by integration. So this is a complex number, and this gives me a pairing between these two vector spaces, which is actually a perfect pairing. Sorry. Okay, so that's one theorem that one needs to sort of formulate the basic results of Hodge theory. As I said, this doesn't really use the complex structure on X. If you want to bring the complex structure in, you sort of, once you bring the complex structure in, you will be able to understand the right-hand side of this theorem much better. And so let me record kind of one consequence of it, which is Hodge's theorem. And so for Hodge's theorem, I want to make an additional assumption that X is actually Kähler. So And so, I mean, if you like, this kind of most important example for the purposes of this talk is projective varieties. So, take a subset, a complex manifold that is a submanifold of complex projective space. And then it acquires a Cayley structure from the Cayley structure on projective space. And these are actually algebraic varieties. And later in the talk, I'll focus attention on algebraic varieties. And so what does the theorem say? The theorem says that when X is scalar, you can kind of refine this isomorphism by refining the right-hand side by giving it a canonical decomposition into direct sum of pieces. So then there exists an natural isomorphism between Hn of x comma c and the direct sum over p plus q equals n of what is called HPQ of x. And so what is HPQ of x? These are the forms, or these are cohomology classes that can be represented by forms which, when you pick local coordinates, have kind of p holomorphic directions and q anti-holomorphic directions. So there's p dz's and q dz bars. And so that you can always define just by virtue of the complex structure. But the fact that x is scalar tells you that even when you pass to cohomology, those pieces kind of stay independent. They don't talk to each other. So you actually get a direct sum decomposition. And you can sort of go further by understanding the left-hand side or the right-hand side. These HPQ spaces entirely in terms of the complex geometry of x as follows. So moreover, we have HPQ of x is identified with HQ of omega p of x. And so here I'm using the language of sheaves. So omega p of x is the sheaf of holomorphic p forms on x. And once I have a sheaf on a space, I can talk about its cohomology. And so this is the cohomology of the sheaf of holomorphic p forms in degree q. And that turns out to equal HPQ. And this kind of gives us a very close connection between the topology of x, which I sort of measure in terms of singular cohomology, and something that is kind of manifestly related to the complex geometry of x. So this is the holomorphic function theory of x. Right. Okay, and so why is this useful? So I mean, it's useful for many things. One thing that it tells you is that this kind of abstractly defined vector space over the complex numbers actually has this canonical decomposition into these HPQs. And so you can use this to sort of study, for example, the properties of maps between algebraic varieties or maps between complex manifolds. If you had a map between complex manifolds, you would have to respect this decomposition. And that gives you some kind of extra leverage to study these objects. I don't really want to go into complex Hodge theory too much in this talk, so let me just record the following corollary of this discussion. So one consequence is that if x is projective, meaning I'm in this setting, so it's a subvariety of projective space, so then a priori it's defined by analytic functions. There's a theorem, Chow's lemma, tells you that it's actually defined by algebraic functions, so it's an algebraic subvariety. And in this world of algebraic geometry, where things are defined by algebraic equations, you can calculate this entirely in the setting of algebraic geometry, meaning without ever leaving complex geometry. So for example, if I give you the equations that define x inside projective space, you could put that into a computer, and the computer would tell you what the dimensions of these vector spaces are. It's kind of a very algebraic calculation. And so one offshot of this is that if x is projective, then we can calculate the Betty numbers, so the dimensions of the left-hand side. Purely algebraically. By this I mean in terms of the equations that define x. You don't have to sort of think about how you would normally calculate singular cohomology, which would involve, for example, choosing triangulation of your space and computing some kind of cellular homology. Okay, so these are kind of the basic results that form the starting point of complex Hodge theory, and then of course you can go a lot further. In this talk I want to go in an orthogonal direction, so I want to go towards the p-adic setting. And so let me formulate a question about the topology of x, which is not answered by what I've written over here. So, question is, so let me say in words what I'm doing first. So here, in both these theorems, you're studying the cohomology of X with complex coefficients. So you've lost all the torsion information. If you have a torsion homology class, or torsion singular cohomology class, then you extend scalars to the complex numbers, it just dies. You don't see it. And so the obvious question you could ask is, so let's say I gave you, instead of a singular cohomology class with C coefficients, I gave you a singular cohomology class with torsion coefficients. So let's say the coefficients in the finite field Fp, the P elements. So does such a class have some algebra geometric meaning? Is there a way to think about it in terms of differential forms, for example? Hodge's theorem tells you that if instead of Fp I had C, I can think about it in terms of these HQ omega P's, which have the completely intrinsic algebra geometric meaning. But the torsion coefficients, you can't do that. And so one goal of this talk is to describe a partial answer to this question that sort of realized over the last few years is that, well, it's partially yes. And the meaning I want to explain is the following. So yes, we can think of it as an I-form again, but on something which now has to live in characteristic P, because you have something that's an Fp vector space. So as an I-form on X mod P. And so I'll make sense of this in the rest of the talk. But this is kind of the rough idea that if X is going to be defined by algebraic equations, and you want to study a torsion cohomology class on X, one way to study it is by kind of taking the equations that define X, reduce the equations mod P, and study the geometry that you get in characteristic P. Okay. And so if you want to actually, so now let's try to make sense of this. If you want to do this, you want to be in a setting where X kind of lives, so X was a complex manifold or an algebraic variety over the complex numbers. It was living over a field which had characteristic 0 in the complex numbers. Here I want to reduce X mod P, so I want to be in a setting where I can also reduce mod P, not just live in characteristic 0. And there's an obvious way to do this, which is the p-adic numbers. And so this is kind of my segue into p-adic Hodge theory. And really, this is studying some kind of integral phenomenon. So it's kind of the answer is going to naturally be in terms of integral p-adic Hodge theory. But if you want to sort of talk about integral p-adic Hodge theory, you first need to understand rational p-adic Hodge theory. So the rational story is always easier than the integral story. And so first let me tell you what the rational story is. And then maybe in like 15 minutes or so we'll return to this question. I guess I should pause and answer any questions. Okay, so fix a prime number P once and for all. If you want to talk about the p-adic numbers, well, you need to define the p-adic numbers. So this defines for you a field which is called QP, which is the field of p-adic numbers. So how is it defined? It's defined as the p-adic completion of Q. And so what do I mean by this? So if you think about how the real numbers are defined, you first define the rational numbers, then you define the metric on the rational numbers, which sort of is the usual metric. And then you try to complete the rational numbers with respect to that metric to get the real numbers. There's a choice involved, which is the choice of the metric on Q. There are other metrics on Q. And so there's a p-adic metric on Q, which essentially measures how many p's there are that divide either the numerator or the denominator when you divide it in reduced form. So the more p's you have in the numerator, the closer you are to 0. So powers of p are small in this world. Okay, so as a set, for example, you can think of any element here as given by a power series, ai p to the I, which starts off somewhere to the left of 0. So maybe there are finitely many coefficients involving a negative power of p, but most of them involve a positive power of p. But kind of a vague description. But in system field, it's the analog of the real numbers in this setting. And if you want to do geometry, you want the analog of the complex numbers. I mean, in the earlier discussion, I was talking about complex Hodge theory. I wasn't talking about objects that were defined with the real numbers. And so the analog of complex numbers in this setting, I'll call C. So C over QP is a complete and algebraically closed extension. And so here, perhaps you need the first quirk in the p-adic story, which is when you try to construct the complex numbers out of the rational, if you try to construct C out of R, you try to construct the complex numbers and the real numbers, you pass through the algebraic closure, you get a degree 2 extension, and then you can stop. Because it's a degree 2 extension, so it's a 2-dimensional vector space of the real numbers. It's already complete for the topology, and so you don't need to complete it further. But the field QP, its Galois group is ginormous. It's uncountable. And so if I just pass through the algebraic closure of QP, I would get some infinite dimensional vector space. It would not be complete, and so you have to complete it again. And then you might worry that, well, shit, if I complete it, I might have lost the fact that it's algebraically closed. So I want to close it up again, and then you might have to complete it again and keep going. But thankfully, it turns out this doesn't happen. You can stop at the first step. You first pass through the algebraic closure, and then you complete. So it's an elementary exercise to prove that, but it's a very useful fact to know. Okay, so this is our analog of the complex numbers. And now we need an analog of x in the previous discussion. So it's just x. X over C, and instead of saying compact, complex, manifold, I will say kind of the analogous words in this setting. So compact is replaced by proper, manifold is replaced by smooth, and then kind of objects we're talking about are called rigid spaces. So this is literally kind of the p-adic analog of a compact complex manifold. If you don't like this, please feel free to think about just the case of algebraic varieties. So if I have something defined inside projective space by algebraic equations, that will be an example of such an object.
The adjective rigid, can we explain intuitively in some way?
So Tate came up with it. So this is Tate's notion of rigid spaces. I think he used the adjective rigid because the topology on C, on QP is totally disconnected.
So what?
It's totally disconnected, but I'm not 100% sure about that. So let me
slide around. Okay.
It's just a word.
What does it mean?
Sorry?
What does the word rigid mean?
So there's a class of spaces in non-Archimedean geometry. It's called the class of the category of rigid spaces. That's what I'm talking about. But as I said, the example to think about is just projective varieties.
Over QP. Or
Over C.
Over C.
Yeah. So just like every projective variety gives you a complex manifold, but there are more complex manifolds than there are projective varieties. Similarly, every projective variety over here gives you a rigid space, but there are more kind of non-algebraic rigid spaces compared to complex manifolds, compared to projective varieties. Okay. Other questions? Things I can clarify?
Does the notion make sense over C, and if so, what do you get over C? Over the complex numbers.
Does which notion make sense over C?
Rigid space.
No, so there's a notion of rigid space every time you have a non-Archimedean field. So the complex numbers are Archimedean, they're not non-Archimedean. So the notion doesn't make sense there. But there's kind of a uniform way of defining a category of spaces which makes sense over any topological field. And it has the property that if I plug in a non-Archimedean field, I get this notion, and if I plug in the complex numbers, I get the usual notion.
The usual notion being the scheme of finite type, the smooth scheme of
No, complex manifold.
Oh, complex manifold.
Yeah.
Nothing algebraic.
No. So this is definitely not algebraic. So here you want to allow
It's like that analytic space.
these are analytic spaces, right? So maybe I should emphasize that. This is rigid analytic space. So for example, if you think about complex tori, right? I mean, if abelian varieties form some like codimension 1 subset inside all complex tori, and something similar happens here. There's kind of a notion of a rigid analytic torus, and those form kind of a G squared dimensional moduli space. And then inside there, we have these kind of subspaces parameterizing the algebraic ones. Is that okay? All right, so let me sort of tell you what the analogs of the theorems that I wrote down earlier, the Rham theorem and Hodge's theorem, are in this setting. And so I'll sort of straight away formulate the analog of the Hodge decomposition. And there's two statements I can make, so let me make them separately. So first of all, the statement is that there exists a degenerate spectral sequence which is, so it's an E2 spectral sequence, and the E2 page looks like what we have on the right-hand side of the Hodge decomposition. So HP of omega Q, and then there's a small twist here, and it goes to what we have on the left-hand side, which is the analog of singular cohomology in this setting. So this is etale cohomology. It's etale cohomology with coefficients in this field C, and it's literally the analog of singular cohomology. So for example, if your X was actually a projective variety, and you were evil, and you fixed an isomorphism of this field C with the field of complex numbers, abstractly you can find such isomorphism of fields by Zorn's lemma. Then the thing I'm talking about over here would just be the usual singular cohomology of the corresponding thing on the complex number side. So it's something we know.
It's immoral.
It's immoral, but this thing is not. This thing you're allowed to talk about without making any choices. And then the left-hand side is similar. So omega Q of X is the sheaf of holomorphic well, instead of saying holomorphic, I would have to say rigid analytic, because that's the notion of function I'm using. So it's the sheaf of rigid analytic Q forms on X. And this thing over here is called the Tate twist. And it essentially records a Galois action. So if your X, instead of being defined over C, was defined over a smaller field, such as QP, then both the objects you're talking about on the left and the right would have an action of the Galois group of C over QP. And the statement is that the spectral sequence is going to be equivariant with respect to that action if you put in this twist by a character, which is called the cyclotomic character, or Tate twist. But again, you can ignore that.
The Abelian group action, right?
No. The Galois group is not abelian.
But that action doesn't factor through Abelian action.
For the character, it does, because it's a one-dimensional. Yeah. But on the right-hand side, it doesn't factor through any one dimension, through the abelianization. It's an interesting representation of this group. And so what this implies is that you get a non-canonical decomposition. So it's a degenerate spectral sequence, which means that what you have over here is a direct sum of the corresponding entries that show up over here, but only after making some choices. You can't sort of say that canonically. So you get a non-canonical Hodge decomposition.
So, a minute ago you said there was a way to generalize this and include complex manifolds, which is what you get over the complex numbers. But this it doesn't hold over the complex numbers, so this theorem does not generalize to that kind of case.
Correct. This theorem is very specific to the non-Archimedean context. Also, so this is an E2 spectral sequence. The Hodge to Rham spectral sequence is an E1 spectral sequence. So this is not a generalization of anything familiar on the complex number side. Some of the filtrations here go in the other direction, right? If you work over the complex numbers, singular cohomology with coefficients in the complex numbers maps to the cohomology of the structure sheaf, because you can put the constant sheaf inside the structure sheaf. Here the map goes in the other direction.
Did you reverse P and Q on purpose then, or is that just a mistake?
No, it's an E2 spectral sequence. I think this is the correct indexing. That's what I'm saying. So in the Hodge to Rham spectral sequence, P and Q are switched.
Okay, so it does switch P and Q from all.
Yeah. And then the second statement is so this is slightly dissatisfactory compared to the complex analog because I said it's not canonical. You can't really say that this side is a direct sum of the groups occurring on this side in some nice way. The second statement is that there is a setting in which you can say this. So if you make a further assumption that X is defined over something like QP, so assume X is defined over a finite extension of QP. So this field C is huge. There are lots of finite extensions of QP sandwiched between QP at the bottom and C on top. And so a sphere max is defined over one of these finite pieces rather than all the way up the tower. So then you can refine this to an actual decomposition. So then there exists a canonical isomorphism which goes Hn of x comma c is isomorphic to the direct sum of p plus q equals n, hp x omega q, and then I have to put in this twist. And so this is called the Hodge-Tate decomposition.
So Tate proved this.
Yeah, I'll comment on the history in a second. It's called Hodge-Tate because Tate conjectured this, and because of the Tate twist showing up over here. You can deduce part 2 from part 1, essentially. The observation is that when you have this kind of action of this big group, the Galois group, if you're defined over a smaller field, you have an action of this Galois group. And on the left-hand side, the pieces are showing up with different Tate twists. So the differential goes between things which have a different Galois action. There's no room for the differential. So the differentials are just 0. And they're somehow canonically 0. And you can use that to deduce this theorem from this theorem. Right, so I wanted to say something about the history of the subject. And this is a summary of somehow like 20 or 30 years of work. So I think the story starts off with the work of Tate, where he observed that something like this was true for abelian varieties, and then he conjectured the statement in general. This was sort of, so Grothendieck took this and kind of, he generalized it even more to a statement that I'm not formulating over here, called the crystalline comparison theorem. And this was kind of made more precise by Fontaine, who instead of saying that there exists a functor from one side to the other side, actually told you what the functor was, and then you had to prove that it worked. And so once Fontaine formulated his conjectures, there was a whole flurry of activity trying to prove it. So the first, I think, first theorem in the area was the proof of this theorem by Faltings in the late 80s. And then different people gave a proof of this theorem over the years after that. So there's a proof by Fontaine, Messing, Bloch, Kato, and Tsuji, which use something called symptomic methods. There's a proof by Riesch and Niziol, who uses algebraic K-theory. And there's a proof by Balanson from like 6 years ago, which uses derived algebraic geometry. But they all kind of prove part 2 of the theorem. So no one really confronted what happens if you work all the way on top rather than at some finite levels. Until recently, when Peter Scholze wrote his PhD thesis, and he sort of proved the existence of this spectral sequence in this generality in his PhD thesis. And then the degeneration was proven recently in a paper we wrote together with Matthew Morrow a few years later. So that's kind of, I didn't want to write all of that, but I hope I don't forget any names. Okay. I wanted to make one sort of remark on this, which is maybe slightly surprising, is that in the complex geometric Hodge decomposition, there was this assumption that X is scalar. There is no analog of that assumption over here. So there exists no scalar assumption. And I think this is something that we don't really understand why yet. So there are kind of standard examples of complex manifolds for which the Hodge decomposition fails, like the Hopf surface, and it's not possible to write down p-adic analogs of those manifolds. Like, there are lots of techniques for constructing kind of p-adic or rigid analytic analogs of constructions over complex numbers, but they exactly don't cover the example of the Hopf surface. So
do you have examples where it doesn't collapse at E1?
Well, no, it's degenerate.
No, but 4. It gets, is E1 equal to E2?
There is no E1. It's an E2 spectral sequence.
Well, but in the Taylor case, that's the corresponding spectral sequence collapses at E1.
So this is not the analog of that spectral sequence. That's a different spectral sequence. That sort of, the E1 spectral sequence is the Hodge to de Rham spectral sequence, which converges to de Rham cohomology. And in this p-adic analytic setting, there is no isomorphism between etale cohomology and Rham cohomology on the nose. You have to go up to some big field of p-adic periods to get an isomorphism. So, yeah.
But then, since there's no analog, why do you ask for the Taylor property, what it means and so on?
Well, it doesn't make sense here, but it makes sense there.
Oh.
Like, you can just ask, is the nth Betty number the sum of the HPQs with p plus q equals n? And that's a numerical statement that's true of the complex, that's true in the p-adic setting and not in the complex setting. Another quirk is, which maybe I'm not writing, is that, so in the complex setting, you also have Hodge symmetry. HPQ is HQP, just by virtue of how things are defined. In this setting, Hodge symmetry actually fails. So the Hodge decomposition is true, but Hodge symmetry is not true. And so it's kind of, some things are better, some things are weaker.
So you don't get that the odd Betty numbers are even in this case?
Correct, it's not true. There's a student of de Jong who in his thesis has formulated a conjecture for when that should happen in the p-adic setting. So he has a conjectured analog of the Kähler condition in this setting, but I think they're very far from actually knowing anything about it. Okay, but I want to sort of mention one corollary, which maybe people find interesting, even if you don't care a priori about the p-adic numbers and so on. So this is a consequence over the complex numbers you can deduce from knowing this theorem over here. So the corollary says the following. So let's say x and y are birational, Calabi-Yau, smooth projected varieties over the complex numbers. So this just means it's a complex manifold sitting inside projective space. Calabi-Yau means that the canonical bundle is trivial. And birational means that there is a big open subset that they are identified. So they have the same field of meromorphic functions, for example. And the corollary says that in this context, you can prove that the dimension of HPQ for x is the dimension of HPQ for y. And so this is a result that, again, due to many people. So let me sort of say a little bit about it. So I think this was a conjecture. I'm not sure who to attribute this conjecture to. But there's kind of a consequence of knowing this statement is the statement that the Betty numbers are the same on both sides by the Hodge decomposition. And so the Betty number statement was first proven by Bhatt. And the way Bhatt proved the Betty number statement was by sort of using the Bay conjecture. So you sort of reduce everything mod p, you do some point counting, you see that the number of points are the same on both sides, and the Bay conjectures then tell you that the Betty numbers are the same. And then a few years later, Ito noticed that if you sort of take what Bhatt did and upgrade it to a statement about not just the point counts being the same, but certain Galois representations being the same, then you can input the Hodge state decomposition to immediately conclude that the Hodge numbers are the same.
Wow.
But in between those two, Kontsevich came up with motillic integration, which also proved this statement. So somehow, I think the fact that people missed going from the Bhatt statement and using p-adic Hodge theory to this statement was useful because we now know about motillic integration.
You can't prove something like the diagonal induces an isomorphism or something, like some sort of functorial thing, because the motillic stuff is like an Euler characteristic argument. This is sort of...
Right, so I don't think you can prove that. I think the way Bhatter's proof works is he wants to compare point counts on x and y by kind of, you sort of find something common that resolves the map, and then you use kind of p-adic integration to relate point counts here to point counts here.
Yeah, what I mean is your method, your corollary.
It's not my corollary, it's...
No, this one.
You said it's a corollary of...
Yeah.
Oh, I see.
This
okay.
is Ito.
Oh, this is Ito. Oh,
Yeah.
I see. Oh, okay. Okay. I misunderstood.
I'm just trying to give it history, yeah.
When was the Betty number thing proven?
Sorry, I don't remember this. I think it was in the 90s at some point, but probably someone here knows better than I do.
Unbelievable.
Okay, right. And of course, I mean, so these results in p-adic Hodge theory, so this Hodge state decomposition has lots of other applications in number theory, but I'm not getting into any number theory in this talk. Instead, I want to now go back to this question I had earlier about how to sort of geometrically see mod p homology classes. And so this is integral p-adic cost theory. And essentially what you want to do here is you want to understand on both sides of this theorem what happens if you sort of use integral structures. So, I mean, this is roughly the cohomology of coefficients in C, or sorry, literally the cohomology of coefficients in C. It's induced by something that is defined by the ZP coefficients. So integral coefficients, not just rational coefficients. If you want to sort of compare it with something integral on this side, you need to have an integral structure on X. Right? H00 is functions on X. And so you need some integral version of functions on X. So you really need an integral avatar of X. You need some kind of a space X where it makes sense to both invert P and kill P to go from between characteristic 0 and characteristic P. So that's kind of the subject of integral p-adic cost theory.
It makes sense to be able to do both. You
Right.
can't do both.
Right. You need an X where you can do both.
Not
So
at the same time.
let me write. Yes, not at the same time. Otherwise you get 0. So fix it again, the same setup. Fix the prime P, and then I have my QP and C as before. So if you want to be in a setting where you can both reduce mod P and invert P, you sort of use the following observation, which is that if you look at OC, which is the set of all p-adic complex numbers whose absolute value is less than 1, this closed unit ball inside the field of complex numbers, because this field is non-Archimedean, this is actually a ring. It's not just a field. I mean, it's not just a set or a space. And in fact, it's a nice ring. So it's a valuation ring. And so a valuation ring is, in particular, a local ring. So it has a unique maximal ideal. And the statement is that when you sort of go mod the maximal ideal, you get something of characteristic P. So there's a valuation ring whose residue field K has characteristic P. And this is very easy to see. So the maximal ideal of this ring is exactly the open unit ball. So the closed unit ball is the ring, and the open unit ball is the maximal ideal. And the prime number P, remember in the p-adic topology, the prime number P is small. So it doesn't have absolute value 1, it has absolute value strictly less than 1. So it's in the maximal ideal. And so when you kill the maximal ideal, you have killed P. And so you have a ring of characteristic P. And so now this is a ring where you can both invert P and kill P. And so we really need to be working over this sketch. And so therefore, you get the following picture, where you take OC, and if you kill P, you go to this field of characteristic P. If you invert P, you go to the fraction field, which is just the p-adic complex numbers again. Because if I have any p-adic complex number, I can scale it by enough powers of P to make its absolute value less than 1. And so we're going to sort of, our geometric object was first living over here, but now we're actually going to assume that it lives over here. So it makes sense to kind of go in this direction as well. Okay, so the technically correct way of saying that is the following. So assume X over C has what is called good reduction. And so roughly what this means is, for example, if you think in terms of algebra,
OC.
good reduction over OC, yeah. So, for example, if you had something defined by one equation, the fact that the space was smooth at a point is a statement that the derivative of that equation is non-zero at that point. But non-zero just means non-zero in C. It could very well be that you have an element here, which is non-zero here, but becomes 0 here. It would be in the maximal ideal. And so the good reduction means that that doesn't happen. And that's the generic situation. If you start out with something defined with coefficients in the rational numbers, then most primes are primes of good reduction. And the sort of practical consequence of this is that there's a cousin to X that lives over here. So X over C specializes to something over here, which is smooth proper. Algebraic variety. So you can relate this characteristic 0 space X to an algebraic variety in characteristic P. You just, naively speaking, you just reduce the equation mod P. And so,
Are you defining X over OC first?
well, I'm trying to suppress that by saying I'm assuming that it has good reduction.
So that means you can live to
Right. So what I really should say is that there's a smooth and proper scheme over OC whose generic fiber is X and special fiber is XK. Yeah, thanks. Okay, and so remember, what was the question I started off promising to address? It was to understand mod P singular or etale cohomology classes on this X. And the answer is going to be that it's related to some kind of a Rham cohomology class here. So let me sort of formulate one version of the answer. So this is this joint work I mentioned earlier. And let me just formulate the numerical statement. So the numerical statement is that the dimension of my singular, or I guess etale cohomology with mod P coefficients is at least bounded above by the dimension of the Rham cohomology of this characteristic P space. And so if you see kind of a non-trivial mod P homology class on X, it translates to some kind of a non-trivial mod P I form on this characteristic P variety.
Not only the dimensions are equal, but there's kind of the information there is on the right. The information on the left-hand side is on the right-hand side.
I'm not sure what you mean by that.
Well, just saying that it doesn't say that anything on the right-hand side is related to anything on the left-hand side.
Right.
Unless there's a map or something.
There's no map.
But the information is somehow there anyway.
So there is a common thing that has information for both these objects, which I am not writing. You can tell me my course, so you know. You already know everything.
Yeah, but
There was no integration pairing as.
There is no kind of integration pairing in some kind of easy sense. There are kind of p-adic period rings, and there are maps you could write down that you might call p-adic integration. But the integration happens not with coefficients in the p-adic complex numbers, but actually a one-dimensional thickening of this. So there's a p-adic period ring, and you integrate the coefficients in that ring. So I think this is the easiest numerical statement one could make. And there's a similar kind of statement with mod P to the n coefficients as well. Let me not write it. So let me instead give an example of the type of information that's being captured here. So let's say the prime key is 2. And X over C, this thing I have on geometric object X is an Enrique surface. And so the only thing I need about Enrique surfaces is that the fundamental group is a Z mod 2. And the universal cover is a degree 2 map, and it's a K3 surface. And so, because X is an Enrique surface, if you think about what H1 is of X with F2 coefficients, this is always just harms from pi 1 into F2. But pi 1 is Z mod 2, so this is also a one-dimensional vector space. In particular, it is not zero. And so what does the theorem tell you in that case? It tells you that the left-hand side is non-zero, so the right-hand side also should be non-zero. So the theorem implies that H1 of the Rham cohomology of this Enrique surface in characteristic 2 is also non-zero. And so this was actually something people have already seen before. So this was computed by William Lang and UC. But the proof was very different. So there's a classification of Enrique surfaces in characteristic 2 by Bombieri and Mumford. They fall into 3 types. and they kind of run through each of the types, compute what happens in each case, and in each case you get a non-zero answer. And so this is regarded as a pathology of de Rham cohomology in positive characteristic. And so maybe what the theorem is saying is that every time you see torsion in singular cohomology in characteristic 0, the corresponding de Rham theory must have these pathologies. They're unavoidable.
Why is it a pathology?
Because the answer looks different than the answer you're used to from characteristic 0.
Oh.
I didn't come up with a name. I think Mumford is the first one to call it a pathology.
Doesn't seem like a defect, does it? Seems like plus of the theory.
I agree. And here's maybe a positive corollary consequence of this, which is you get a criterion for when there exists p-torsion in singular cohomology in terms of what's happening in characteristic p. So if the dimension of the de Rham cohomology in characteristic 0, so the ith Petty number, is equal to the corresponding number in characteristic p. So this is over in characteristic p, this is in characteristic 0. Then a slightly better version of that theorem will tell you that in degree I plus 1, there is no p-torsion. So if you have an algebraic variety and you want to test whether or not its cohomology is p-torsion in this degree, it's enough to compute the dimension of the de Rham cohomology of its mod p reduction and see that it equals the number you started off with.
Any chance that that will only it, or maybe for all I that holds is, there's no p-torsion for all I and that holds?
No, so that's not true. Right, so this is one thing I should have said, which is that the inequality can be strict. There are examples where it's a genuine inequality, so those two numbers have no chance of being equal. And in the examples where we know whether those two numbers are not equal, what happens is that you have two objects in characteristic 0, which give you the same object in characteristic p when you reduce mod p. One of those has no torsion in its cohomology, and one of those does have torsion in its cohomology.
The right-hand side is finite dimensional.
Yeah. It's a finite dimensional vector space of this field. It has contrariability in the Schmidt formula and so on. Okay, and so the remaining 10 minutes, I want to explain where this theorem comes from. And essentially, let me sort of say in words what happens. You're trying to relate these two cohomology theories. Etale cohomology that p coefficients, de Rham cohomology with k coefficients. You want to prove a dimension inequality. The easiest way I can imagine proving this is by showing that there's a map in one direction, which is either injective or surjective. And then you would get a dimension inequality. But this actually is provably not true, in the sense that, I mean, of course it's true because they're vector spaces, but there's no functorial way of doing this. So for example, there's a mod p squared version of this theorem, once you make sense of a mod p squared version on the right-hand side. And there are examples where the left-hand side looks like a z mod 4, and the right-hand side looks like a z mod 2 cross z mod 2. So for length reasons, the inequality is okay, but there's no way you're going to have a map that witnesses the length inequality. And so you need to search for a different mechanism for proving an inequality between numbers or dimensions of vector spaces. And I know essentially only one other way of doing this, which is to think of families of vector spaces. So if you have like a family of vector spaces parameterized by some line, then what you would expect is that the generic member of the family has some rank, and then at special members of the family, the rank goes up. Like the vector spaces could be, for example, the cokernel of a matrix, and then the rank goes up at the points of the matrix is singular. And that's actually what happens here. So what we do is we construct a cohomology theory that lives over a one parameter base. And so the generic value of the cohomology theory is this side, and the special value of the cohomology theory is this side. So let me now write those. Strategy of proof. And this is very vague. I just want to formalize this idea. So I need a one parameter base over which I do this specialization. So I work over this ring of formal power series in one variable u over fp. It's a discrete valuation ring. the DER. And actually, let me call this A bar, because later there will be a mod p to the n version of this as well. And so the strategy is to construct a cohomology theory with coefficients in A bar. So this is valued in finitely generated A modules. With the following two properties. So for generic values of the parameter, so namely when you invert u, you're going to get singular or etale cohomology. So first is if I take A star A and I invert u, I call it A bar, sorry. This is the singular cohomology of X, so that two coefficients. And then there's an issue, which is that they live over the wrong rings. This has coefficients in FP, and this guy has coefficients in the Laurent series field. But you just formally fix that. In particular, the dimension of this vector space is the same as the dimension of this vector space. And then the special values of the parameter are when u equals 0. And so at u equals 0, what you have is you have a short exact sequence. It's some kind of a universal coefficient statement. So 0 goes to A star of A mod u, which sits inside the Rham cohomology I'm trying to understand. And then the co-kernel is torsion in degree 1 higher. But in particular, the dimension of the generic value of this vector space, sorry, of this module, is this guy. And at the special values, the size of this module is a lower bound for the size of this guy. And so you immediately combine these two to deduce that the dimension of this one is less than the dimension of this one. So you use, for example, the classification of modules over, finally, over a p-adic.
The left-hand side means you invert mu, is that what you mean?
Yeah, that's 1 over u, yeah, invert u. So instead of living over our series, I live over Laurent series. So I ignore all the u torsion. And so A plus B plus classification of modules over p-adic imply the theorem. And so, right, so the important takeaway is that you have to construct this cohomology theory, which is living over this space, and once you have these relations, you get the statement that you want. And so in my remaining 5 minutes, I want to explain what this theory looks like by just essentially drawing a picture. And so, in fact, as I said verbally, you really define a theory not just over A bar, but the mod p to the n versions of A bar as well. So over Z mod p to the n power series u, you still get something, not just mod p. And you can pass all the way to the limit and construct something over Zp power series u. So in fact, you construct A star A, which lives in finitely generated A modules, where A is this ring, Zp power series u. Not just Fp. So Zp is the p-adic integers. So if I reduce mod p in this coefficient ring, I get Fp. So A mod p is A bar. So we have an integral lift of this mod p theory. And so here's kind of what the picture of what this module looks like. And so what do I mean when I draw a picture of a module? So I'm using this algebraic geometry dictionary of saying that I can think of a module as a coherent sheaf from the spectrum. And so the spectrum of this ring is an arithmetic version of the affine plane. So it has two parameters. One is the u parameter and one is the p parameter. A module of this is a abelian group with an endomorphism u and an endomorphism p. Well, p is just multiplication by p, but you think of it as kind of two distinct endomorphisms. And so then you can sort of localize, whenever you have if you have a vector space with two commuting endomorphisms, you can think of that as sitting over the affine plane, where the fiber at the point A comma B is the subspace where kind of the eigenvalue of the first parameter is A, and the eigenvalue of the second parameter is B. So the A eigenspace and the P eigenspace. And so over here, I have the P and the U coordinates, and so let me make sure I do the right direction. So I want to call this the U axis. I want to call this the P axis. And so when P equals 0, I'm living on this part of the picture, and that's what this theory over here is describing. And so what it's saying is that if I localize away from U equals 0, so if I localize away from this point, in this part of the picture, I essentially have kind of mod P singular cohomology or etale cohomology. And then something interesting happens as you sort of go closer and closer to U equals 0. And then when here I said that U equals 0, I essentially get Rham cohomology. And so if you think about, if you sort of do this theory, not just mod P, but mod P to the n and all the way in the inverse limit, you actually end up getting the Rham cohomology over here somewhere. So this is the line U equals P to the P. And here you have the Rham cohomology of kind of the integral model X. So I set X as coefficients in OC. So you can do this Rham cohomology with coefficients in OC. And that lives over here. And so when you go all the way over here, you have the Rham cohomology of the special fiber, which is part B over there. And then there are sort of other specializations in this picture, like I can restrict to the U equals 0 axis of the P axis, or I can restrict the intermediate parts of the picture, and I get different cohomology theories, some of which have names and some of which seem to be new. But I think I'm essentially out of time, so I will just stop here. Thanks.
What is the cohomology of rigid analytic space?
It's defined in the same way as the Rham cohomology of a complex analytic space.
What is the differential form of
So there's a notion of a function on a rigid analytic space. You heard my talk yesterday, right?
Yes.
So that notion of a function, the affinoid algebras, those are the basic functions in your space, and then you can talk about forms and two forms and so on built from that notion of function. Yes?
Just very naively, do people talk about child groups in this context as well?
Yes?
This, like, which cohomology groups in your picture have associated child groups?
Well, I usually think of child groups as something that, so an element of a child group has a realization in any cohomology theory, right? It's some kind of universal cohomology theory. And so that's true over here. So you can realize the child groups into this theory. And when you specialize to these various parts of the picture, you get the corresponding cycloclass maps for those cohomology theories.
I mean, is the image of the child groups expected to depend on the, be the same for the different cohomology theories?
Rationally, yeah. Integrally, I'm not sure. Like, I think integrally it could happen that the image is bigger over here, but smaller over here.
When you have a circle action in the space, and you look at the fixed points, the cohomology kind of looks like that formula on the right up there. Some kind of localization, some symmetry at the fixed point. Is that in the picture?
That's in the picture. So there's a construction of this cohomology theory through topological Hodge homology. And in that construction, the U parameter really comes from the cohomology of the circle.
Any other questions? Okay, second speaker.